There's just a little impromptu Gets video. I have one of these emergency lights that I modified last year. Actually, some of these I've had for a long time, but they both died, or they were dead when I got them. Well, I got them for very little money. Actually, one I think was free because it was dead. They originally took 6-volt, 4 ampere hour lead acid batteries, fairly standard for small, cheap emergency lights like this. And I happened to have been given a crap ton of some obscure Chinese brand drill batteries that the place that was selling them didn't have the drills for. So I got well over a dozen things and hundreds of these, I think over 200 of these nickel cadmium sub C cells for free. So I just cobbled together a battery with 15 of these cells. It's 3 series strings of 5. They had a 6-volt 3.9 ampere hour battery, although in this application it probably has more capacity than the original one did because of this little thing called Poincare law, which, long story short, means that the effective capacity of a battery bank is reduced as the load on a given battery relative to its size is increased. That's why, for example, things like deep cycle batteries are commonly rated, or deep cycle lead acid batteries are rated at something like a 20-hour rate, although some manufacturers, to be oddballs, rate them at 24 hours. Like, for example, a 100 ampere hour battery at a 20-hour rate would be discharged completely if you were to draw 5 amperes on that if you were to put a 5 ampere load on that battery for 20 hours. Of course, obviously, you wouldn't do that because that would effectively kill the battery, because you never want to drain a lead acid battery down to the last 10% or so of its charge capacity, although that is still really pushy and it's probably going to adversely affect the life of the battery. But anyways, nickel cadmiums are much better cells and batteries in terms of those really severe discharges, and they've also got much better performance under high discharge currents, which is why they're commonly used for tool batteries. So anyways, that's just this little thing, a jig that I cobbled together, and of course, obviously, probably going to modify this to fuse at some point, but that's why I taped the ever-loving piss out of both of these connectors just to keep anything from shorting out, because I'm not happy to happen. And the reason I had to do this impromptu teardown thing is because this relay has failed. The normally open contact on it isn't working. I think this was a problem with this light when I got it, but just actuating the relay many hundreds of times. I got the thing to work reliably, but now it's of course stopped working again, because you can see right now it's off because this thing has the ability to shut the lights off, and it also has the ability to only have one lamp head working instead of both. So on the other lamp head, or the one that's on in one lamp head mode, I've just got I think a number 259 lamp. It's only about a 1 watt or 2 watt 6-volt indicator lamp. So, but anyways, if I turn it on, you can hear that the relay engages, but the lights are not turning on. So yeah, he's dead. But this is a fairly standard form factor relay, so I'm just going to be replacing that with probably next Jameco or DigiKey order. I'm just going to get a compatible relay, and I'll probably get 2, just because I expect the other one to fail. See, best tall, nice Chinese quality, and paper laminate PCB, normal crap. And of course, this is the test switch. There's a 1/4-inch fast-on terminal insulated with a rubber grommet, and the way the test circuit works is that the leads on the charging LED are bent so that one of them touches the this terminal, and that is the test switch. Somewhat amusing, but anyways, and then there's this device, gate anode cathode. That is actually a silicon-controlled rectifier. That is not a transistor, but that is actually the charging circuit. And the way this charging circuit works is that the actual charge supply is 6 volts AC, which is rectified by this Gratz bridge. Obviously, it's got provisions for an onboard transformer for ones that be fed with mains, but this is just bodge wired in this barrel connector, because the thing is externally supplied. But anyways, the way that works is that forms in effect a variable conducting, or a variably conducting rectifier, very similar to the way most light dimmers work with just a triac phase cutter. So it would be a phase cutter. And the way it works is that the SCR is acting in effect like a dimmer on the unfiltered rectified DC. And what it does is, as the potential of a battery increases, meaning it's getting more and more charged, that SCR conducts for less and less and less of each half cycle. When the battery gets fully charged, it stops conducting at all, except for probably one little pip at the end just to provide a base, or a maintenance charge on the battery. But and there's just some other miscellaneous transistors and passives which form the logic for the mains failure detection circuitry, which turns the relay on. And pretty much it. Fairly simple, cheap emergency light. And also, of course, be careful if you're trying to do this, because, again, risk of shorting, fusing, blah, blah, blah. Miscellaneous not happy, because one of these things could probably provide a short circuit current of several tens of amperes, which would cook even the, I think, 18 gauge wire or whatever I used. Yeah, 18 gauge there, and I used similar stuff, because this is wire that I had lying around, but, yeah. That's also why I taped the ever-loving piss out of this thing, because these are metal brackets, even though all these points, all these nodes in the battery would be at the same potential. I just taped the ever-loving piss out of the thing just to be on the safe side in case something would eventually touch these, so both of these should, in theory, be floating. Right, I think there's probably, but I might modify that with a bit of extra tape, but yeah, just another random guts video.